All right, so we're going to start off by finishing up a couple of problems we didn't get to in 6.1, and then we'll take a look at a 6.2 part 1, and then we'll look at 6.2 part 2. So we did example A. Let's look at example B. All right, so they're giving you a coordinate. Remember, that's the whole goal. You gotta either be given it or you gotta find it. In the next problem, we're gonna have to find it. So this is x, this is y. So the directions are to find the 6 trig functions for the angle represented by this coordinate. Now, we've got some numbers here with square roots. So we have no idea what angle this is, and we don't need to know, right? It's kind of like we're just going to describe a bunch of things about the angle, but we're never going to know how big the angle is. Right? It's kind of like if you met someone or you saw someone on the street, someone said, describe the person you're seeing. You can describe them without knowing their name. You describe their hair color, eye color, how tall they are. You don't need to know their name to do it. That's kind of what we're doing here. Describing a bunch of things about an angle that we don't even know how big it is. Right, so let's start with the sine. Okay, so sine and cosine, those are the two simplest ones. What's going to be the sine here? Click.
The y.
The y, which is?
Square root 3 over 2.
Yep. So sine is square root 3 over 2. Okay. How about my cosine? Okay. X, which is? 1/2. Now, to get the tangent, all you have to do is y divided by x. So what I do is I kind of imagine putting a division line right there, and now you're going to divide sine by cosine. It's basically how you get tangent, sine over cosine. So when you divide them, they each have the same denominator. So what happens to the denominators because they're the same? They cancel out. Some people flip and multiply by the reciprocal. You could do that too. But whether you multiply by the reciprocal or just notice the denominators are the same, they cancel out. All right. So all you're left with is square root of 3. So sine, cosine, tangent. And now, Gabe, what do I do with those 3 to get the next 3?
It's like the opposite.
So like -1/2?
No, it's reciprocal.
Reciprocal, okay. Yeah, so we flip it. What's the name of the function we flip? When we flip sine, what's the name of the function you get? Cosecant, yep. Cosecant. All right, so we flip it, 2 over the square root of 3, but there's something wrong with that. It's not like we did anything wrong, it's just this naturally happened and we got to fix it. Yep.
You can't have a square root on the bottom.
You
so
can't.
You multiply square root 3 over square root 3.
Yep. So you're going to multiply by square root of 3 over square root of 3. And that gives you 2 root 3 over 3. What's the name of the function you get when you flip cosine? Secant. Now this one's not as bad to flip because there was no roots in the original, so we flip 1/2 and we just get 2. That's not bad. Okay, and then the last one, the function you flip, the function name when you flip tangent is cotangent. So the cotangent equals, and now square root of 3 is not a fraction. We can make it a fraction just by putting it over 1. 1 over root 3, fix it. Same way Emma told us earlier, by multiplying top and bottom by root 3. Okay, from this point forward, I'm just going to fix them. Okay, I'm going to assume that from working with square roots, you know how to fix it. But I'll ask one more time. Any questions on how I did that one? Okay, so from now on, I'll just fix it automatically. Or you can fix it when you tell me it. Okay. So there's the 6 trig functions. They gave you a coordinate. This one's a little different. They're asking me for the 6 trig functions of 90 degrees. Well, knowing the angle is not really helpful directly. what do you need to find out about 90 to do all 6 of these?
You found the point of the circle.
Yes. You want to find the coordinate for where the terminal side of 90 hits the edge of the circle. Right? So 90, that's one where it just goes straight up. Here's your initial. There's your terminal. So what's the coordinates for 90 degrees?
0, 1.
0, 1. Now, this problem, 0, 1, we did it yesterday. It's all the same. It's exactly the same problem, literally the same problem we did. Example 1a. All right. So I'm just going to put C example 1a from there. All right. So the only extra step was finding the coordinate. Any questions on how to get 0, 1? Okay. Let's look at this one. The 6 trig functions of 270. Same idea, Chris. What do I have to find first?
I'm not sure. I'm a little confused as to how you got to your 1 and 90.
All right. Can someone explain how we got the 0, 1? Where does that come from?
The terminal side where it like hits the circle.
And why is it 1? How come it's not like 0, 3 or something? It's a unit circle. So this is the radius. You've gone up 1 unit starting from the origin. So when you go up 1, the coordinate is 0, 1.
Oh, okay.
All right. So we got to do the same thing here. We got to find the coordinate for 270. Where's 270? Where's the terminal side going to hit in this case? Yeah.
0, -1.
Yeah, it's down. 0, -1 is where the terminal side would be. So 0, -1. Now we could go through our values. Sine is y, cosine is x. How about tangent? What's the tangent of 270 going to be? Undefined. It's sine over it's y over x. Anytime you divide by 0, it's undefined. And now we flip them all. So -1 stays the same when you flip it. How about when you flip 0? What do you get when you flip 0? Chris?
Would that be undefined?
0 flips, becomes undefined. So if you flip undefined, you must get 0. One changes into the other. That's it. Any questions on that one? Okay, let's look at this one. You know what? Actually, let's do one with radians. And I'm just going to find, I'll just do the first 3. Sine, cosine, tangent. Right. Just like the last 2 we did, Nate, what's the first thing I got to do here?
Find the coordinates.
Got to get the coordinate. What might make it a little easier to get the coordinate for this one? If people have trouble looking at that 7 pi over 2.
Give her the make it not fraction. I don't really know. I'm just kind of guessing.
All right. What is that 7 pi over 2? What? Like, it looks different to me than all the other ones we've done. We did this one. We did one like that.
Oh, it's radius, not degrees.
Yeah, it's radians. So maybe we change it to degrees. That might make it easier. Well, does anybody remember what? That's a common one. I know that it's multiplied by 7, but does anyone remember what pi over 2 is?
90.
90. So it's 9 times 7. Or 90 times 7. So that's a quick way to change it to degrees. Now, that's kind of big. How could I make this smaller? I want to find an angle that's coterminal with it, but smaller than 630. And this is what we did, I think, on the first day. Yeah, please. Subtract 360. So 630 minus 360 gives me an angle of 270. Oh wait, 270. We just did that problem. So from here on, it's exactly the same question, all the same answers. So I'll just put C example 3. So a lot of times it might look like it's a different problem, but this wasn't. It was the exact same problem we just did. Right, let's look at this one. Find the 6 trig functions of negative 90. Well, this time we've got the opposite problem. The angle there is negative. What can I do to make it positive? And what would it be? Kaylee?
You could add 360
Add 360.
and then it'd be 270.
So it's 270. That's the same question again. It's exactly the same thing. So we'd have all the same answers as example 3. I think it was 3. Yeah. Any questions on that? Okay, so that's the part we didn't get to. I told you it wouldn't take too long. So if you didn't do this part, that's part of what I'll take a look at tomorrow. So on 335, let's just take a look. They ask you in 1, 5, and 8 to just find the coordinate. That's all they ask you to do. So I'd like you to find the coordinate, but then after you find the coordinate, take it the next step and do the 6 trig functions. The sine, the cosine, the tangent, and do the 6 trig functions of those 3. Well, 3 pi over 2. Pi over 2 is 90. 90 times 3, 270. We've done that problem like 4 times, so you already really have this one done. This one you got to figure out the coordinate for yourself. This one I'm giving you the coordinate. And I think we're actually going to look at that today too. That special coordinate. Square roots of 3s and square roots of 2s, they're not just random. Like, you won't see many other square roots besides those 2. And they come up for a certain reason. And I'll show you why today. All right. So let's take a look at part 2. So now what I want to be able to do is, instead of just finding the 6 trig functions of 0, 90, 180, and 270, which we already know how to do, I want to be able to find the trig functions for angles that are 30, 60, and 45, or in radians, pi over 6, pi over 3, pi over 4. So that would be, let's see. So that would be 45, okay, would be right there. 30 would be down there. 60 would be up there. So it's kind of like those 3 points clustered in like the central part of quadrant 1. Okay. Yeah?
What was the pi over 6, pi over 3, pi over 4?
That's 30, 60, and 45. So we're going to figure out how to find the coordinates of those 3 points. And then if you can do those, we can do multiples of any of those angles. If I draw it bigger so you can see it. Oh. If you can do a 30-degree angle, that's 0, that's 90. Well, you can also do this one over here because it's just a mirror image of the one in quadrant 1. So once we figure out the 30, the 45, and the 60, all you have to do is mirror image them into other quadrants. So all the numbers stay the same. It's just sometimes you have a negative in front of the number or in front of both if you're doing a point in quadrant 3. Right, so we'll start off in quadrant 1 though and just figure out what's going on there. Okay, and then we have a little bit of time at the end, and we might have to finish this part up tomorrow. We're going to work with trig identities a little bit. Okay, this is kind of like if you think of like in terms of like a meal, this is like an appetizer for trig identities. we're going to spend a whole week on them at some point. So at first, they're different. Okay, some people kind of like them because there's no numbers involved at all. So you're not really solving equations or graphing. You're not drawing. It's a little different. So we're going to start to work with them, but we're going to come back to them at least 5 or 6 times for different lessons. All right. So don't get super concerned about trig identities today. So let's start off by, well, let's look at this. Looking at a 45-degree angle. Okay, so what I've done is I drew 45-degree angle right there. And that's halfway between 0 and 90. And I want to figure out the coordinates for 45. Because once I can figure that out, then I can do unit circle trig with a 45-degree angle. Now, the way we're going to figure it out is we're going to make a triangle, okay, out of this diagram. Okay, I'm going to make a triangle. So I'm just going to draw a line straight down to the x-axis perpendicular from the point at the end of the terminal side of the angle. So I've just created a 45-degree angle between the positive x-axis and the hypotenuse. Now, we should be able to figure out that angle at the top, too. How big is that angle at the top? Yeah? It's also 45, okay? Because all the angles have to add up to 180. So I've just drawn a 45, 45, 90 right triangle. On the MCAS reference sheet, there's 2 special triangles. This is one of them. So you might already know how to figure out the sides. Okay, I'm going to assume we don't remember it. We'll figure them out, and then once we know them, we never have to figure them out again. We just have to remember them. What kind of triangle is that? The 45, 45, 90. Okay?
Right.
It's a right triangle. Anything else? What's another word you can use to describe that triangle? Yep.
Acute.
Yep, it's acute. No, it's not acute because there's a right angle. There's 2 acute angles. But to have an acute triangle, all the angles would have to be less than 90. Kind of like an equilateral triangle. You want to think of another word yet?
Is it isosceles?
Yes, it's isosceles. And that's the key. What does that mean?
The 2 sides are the same.
Right, 2 sides are the same. So in this case, I already know the hypotenuse, right? Because that's drawn in a unit circle. What's the hypotenuse of the 45, 45, 90 in my circle? 1. Now, unfortunately, that doesn't really help me directly because that's not part of the x or the y coordinate. X coordinate is the length of that side, and the y coordinate is the length of that side. But because it's isosceles, we know the x and the y value here are going to be what? In general, they're going to be the same. So once we find one, we automatically know the other. And we're going to figure out how to find them, assuming you don't remember the special relationship in a 45, 45, 90. A lot of people don't remember it, usually.
Where did you get the 1 from?
Where did I get the what from?
The 1.
The 1, it's the radius of the unit circle. So it's the radius of this circle. Everything is always on a unit circle. All right, so let's figure out how we can get the length of the bottom and the height of the triangle, which are the same. Well, for now, I don't know the length of the bottom or the height. So I'm going to call the bottom x. Now, keeping in mind what we just said, if the bottom is x, how would you represent the height? Yeah, at x, it's the same. Don't pick a different letter because it's not different. and the radius is 1. What formula can I use when you have sides in a right triangle and you're trying to solve for them? Chris?
A squared plus b squared.
What's that?
Pythagorean theorem.
The Pythagorean Theorem. Could you set up the Pythagorean Theorem with what I have in this triangle?
Yes. Because x is the same, so a and b would be the same.
And what would the formula be?
X squared plus b squared equals, or x squared plus x squared equals 1.
X squared plus x squared equals 1. So I have x squared plus x squared, that's 2 x squareds. All right, what would I do next to get x by itself?
Divide 1 by 2.
Divide each side by 2. Divide by 2. So I get that x squared is a half. And how about someone else tell me how I would get x by itself now? Square root each side. So x is the square root of, remember when you square root a fraction, you just do the top and the bottom separate. The top is nice. That's 1. But the bottom is not a perfect square, so I end up with a square root, which I can't leave. So what would you get when you fix that so the root's not in the bottom? Square root of 2 over 2. So in part of tonight's homework, you have a coordinate that is square root of 2 over 2. You didn't have to know, but now you should. This has something to do with a 45-degree angle. Square root of 2 over 2. But again, you don't need to know that to do that problem. All right, so now we know the length of the bottom side is square root of 2 over 2. And the height is square root of 2 over 2. All right, so now if you think of this as your origin, okay, I'll put a circle up here. There's my triangle inside the circle. Starting from the origin, I have to go over and I have to go up to get to that point. So let's write the coordinates of that point. How far over do you go from the origin to right there? How long is that side? Yeah.
Square root of 2 over 2.
Yep. It's the square root of 2 over 2 to the right. And then from there, you go up how much to get to that other point? Yeah.
Square root of 2 over 2.
Square root of 2 over 2. So there's your coordinate for 45 degrees. That never changes. That's always the coordinate for 45 degrees. There's only 3 numbers you need to memorize to do this unit circle trig we're doing today. That's one of the numbers, root 2 over 2. Any questions on that one? Okay, so that's your coordinate for 45 degrees. Root 2 over 2, comma, root 2 over 2. Okay, let's look at a problem that would involve a 30 or 60. So if you had your circle, and let's look at the 30 first. So this is 0, this is 90. That would be about 30. Okay, about 1/3 of the way we're going counterclockwise in quadrant 1. Okay, I'm going to do the same thing. I'm going to make a triangle. The angle between the positive x-axis and the hypotenuse, that's my 30. So the terminal side has been tilted up 30 degrees. How about the angle at the top of the triangle? What would that be? About Kathleen?
C.
Yeah, that would be a 60. So I'm going to ask the same questions I did last time. Well, a little different, but is that an isosceles triangle? Justin?
No.
No. So the problem here is you can't say, okay, well, I'll just let this side be x and this side be x. That doesn't work. They're not the same. So if you say, all right, I'll let them be different letters. Well, now the problem is if you do the Pythagorean theorem, you're going to get x squared plus y squared equals 1 squared. You have two variables in the same equation. You can't solve that. Okay, you can only have one variable. So we're going to have to figure out, we still have to use the Pythagorean theorem, but you've got to figure out one of these first a different way, okay, before you can use Pythagorean theorem. All right, so we know that side is 1. Anyone have a guess what we can do to figure out one of the other sides? It's a little tricky, but it involves making a copy of this triangle. Well, this is one way to do it. And then from there, you can kind of figure out one of these two sides.
I was going to say to find the sine, cosine, and tangent of one of the angles.
All right, so if we knew how to do right triangle trig, you could just say, for example, the sine of 30 is opposite over hypotenuse, and then you could solve for that side. Let's pretend we don't know right, well, we don't, I haven't taught you it yet. So we won't use right triangle trig, something even simpler that like someone in geometry could do. It's a little tricky. Any guesses? Yeah?
You flip it to make a rectangle.
All right, so I'm going to make a copy of this. Let's see, group all this together and make a copy. So you want me to flip it like vertically, up to down?
Vertically and then horizontally.
All right, let's take a look. So flip it up, down, and then flip it, you said horizontally. So to make a rectangle? Okay. Yep, that's a rectangle. Now what would I do?
There's a diagonal formula, something.
Diagonal. Well, we know the diagonal is 1, but we still don't, and we know this side is the same as this side, and that side is the same as the bottom side. I don't think we have enough information. My suggestion is going to be to try to make another triangle out of the two somehow. There's two ways you can make a triangle. One way will work, the other way won't. Right, Nate?
Can you use trig functions to use with that information?
Ask Blake about that.
With the side and a angle, can you get the other?
Blake will talk to you later. Yes, but no. No, no, no. Yeah, he'll fill you. So, any other suggestions about flipping it somehow to do something? And then once you flip it and you see this, it's like super simple. Yeah?
Just flip it and make an isosceles triangle.
All right, I'm going to flip it, and instead of even making an isosceles triangle, I'm going to do something even better. I'm going to make an equilateral triangle. Because I don't know how to do it making an isosceles triangle. I'm not sure where you would go from there. But if you know, let me know. And then maybe I'll learn how to do it that way too. So now I've made an equilateral. What does that mean? I mean, I know it means this is 60, 60, 60. But what else does it mean?
It means that the sum of the two sides that we don't know equals 1.
Right, the sum of this side and this side, they're congruent because they're copies of each other, and they have to add up to 1 because it's equilateral. So if each one of them is equal and they add up to 1, that means each one of them is how long? 0.5. They each have to be a half. Now, we know this side is a half. We can do Pythagorean theorem to get the last side. We don't need the copy of this triangle anymore either. Right. Any questions on that? So it's just a trick to figure out one of the sides by using a little bit of basic geometry. All right. So now call the bottom side whatever you want. You can call it x, and now we'll solve for x. All right. So using Pythagorean theorem, x squared plus, what's a half squared? fourth equals 1 squared. We bring the 1/4 to the other side, and what does that leave me with on the right? 3/4. And now my last step, take the square root, and this one's going to be nice because the square root of the bottom is a perfect square. So it's √3/2. So now we know the coordinates to get to 30 degrees. You travel this far from the origin to the right, so that's square root of 3/2 to the right, comma, and now you go up from that point, ending at the point on the circle, right here. How far up do you go? 1/2, and there's your coordinate.
Is that constant, like 45 degrees?
Yes, it always stays the same, it never changes. So the coordinate for 30 degrees is always √3/2, comma 1/2. Now I said there was only 3 numbers you had to know to do this part of the lesson. Well, √2/2 is one of them, √3/2 is the second one, 1/2 is the third one. You're not going to see any other numbers. So let's see what happens when you try to do a 60. 60 would be up here. Your triangle would look like that. What's the difference between the triangle I just drew and the first triangle? Comparing the 2 triangles that are in quadrant 1. Yeah.
It just looks like it was fourth.
Yeah, it's just been flipped and then kind of rotated, but these are congruent triangles. They are exactly the same triangle. The only thing that happened is now the 30 is at the top, right in here, and the 60 is at the bottom. So what do you think the coordinates are going to be for 60 degrees? Yep.
1/2 and then 3.
Yep, it's 1/2, 3/2. The only thing that's a little tricky about the 30 and the 60 is it's kind of easy to mix up the 2 numbers. Wait, so is this the one where the half comes first, or should the √3/2 come first? Well, look at the decimals. Okay, 1/2 is 0.5. √3/2 is 0.866. √3/2 is a bigger number than 1/2. Bigger. So what that means is √3/2 is always the longer side, 1/2 is always the short side. So when I sketch the triangle, if you sketch it even somewhat accurately, the long side is always the bigger number, √3/2, and the short side is always 1/2. In the other triangle, there's my short side, that's my 1/2. There's my long side, that's √3/2. That's how I remember which one is which. Long side, √3/2, bigger number. Okay. Any questions on that? Okay, so we'll try some examples. We'll start off with some stuff in quadrant 1, and then we'll get into other quadrants as well. So now the questions are just like the ones from the end of last night's homework. Find the 6 trig functions. Okay, so Madison, they've given me an angle of 45 degrees. What do I have to do first before I can do any of these 6?
Find the coordinate.
I have to find the coordinate. This is one we should just memorize. √2/2, √2/2. So you don't have to do any work to find it. We already did all the work. We're never going to have to go through all that again. And now from here, this is actually one of the homework questions. The first part. So let's start with the sine. Gabe, what would the sine of 45 degrees be?
√2/2.
And which one did you pick, just so I know?
The y value.
The y value, yes. In this case, they are the same, so if you switched them, you'd get lucky and it would be okay. But you shouldn't switch them. Okay. Tori, how about the cosine?
√2/2.
Yep. And and that one was from the x. And now the tangent, you're dividing the sine by the cosine, the y over the x. But they're the same. So Chris? Just be 1. So that means the cotangent, that one's quick. Because when you flip 1, you get 1. And now we have to flip root 2 over 2. So when you flip it, you get 2 over root 2, but we have to fix it. What do you get when you fix 2 divided by root 2? 2 square roots of 2 over 2. So that means, what would cancel there? The 2's on the outside. So all you're left with is square root of 2. Now what about the secant of 45? Same thing. Sine and cosine were the same. Secant and cosecant were the same. And there are your 6 trig functions for 45 degrees. Any questions on that one? Not too bad. Let's look at this one. Find the 6 trig functions of 30. Okay, first thing I need is my coordinate. Okay, so now in my head, I know it has to do with a 1/2 and a root 3 over 2. I'm not sure the order. Okay, so what I'll do is just make a quick sketch. 30 degrees, somewhere down there. Make my triangle. And I can clearly see which side is the long side. This time the x is the long side and the y is the short side. So that means my x value is going to be which number? Yep.
It would be 3 square root of 3 over, or, sorry, square root of 3 over.
Yep. And then the y is my short side, and the short side is always what number? 1/2. Okay. Now we just go through the problem. Bless you. Right. So Natalie, what's my sine?
The y value.
Yep. So I have cosine is the x. Tangent. Again, I just like to pretend I put a division line right there and pretend like you're dividing y by x, because that's what you do. When you divide y by x, what happens? The 2's cancel, and you're left with 1 over the square root of 3. And when you fix it, square root of 3 over 3. Don't get rid of the 1 over square root of 3, though. That's going to come in handy in a minute. How about my cosecant of 30? Yeah. 2. So that one's not bad because you don't have any roots in it. The secant of 30. You want to tell me what you get and fully fix the answer if you end up with any roots in the bottom? Yep.
2 root 3 over 3.
Yep, 2 root 3 over 3. Now, when you do the cotangent, you have a choice. You have 2 things that are equal to each other. That's why there's an equal sign. I could either flip the one that's not circled, or I could flip the one that is circled. They're the same thing. Which one would be better to flip?
Not circled.
The one that's not circled. How come?
There's no square root of 5.
Yeah. When you flip it, the root goes to the top, fixes it, and you're done. If you flip the one that's circled, you're going to put the root back in the bottom, you're going to fix it all over again, and you're going to get the same answer. Questions on that? All right. Let's do the 6 trig functions of pi over 3. We're not going to keep doing 6. Eventually, I'm just going to start doing less. But we'll do 6 one more time. What's pi over 3? If you think of that one in degrees. 60. All right. So I think, okay, quick sketch. I actually kind of just think about it in my head, but if you want to make a sketch, you can. 60 is up more towards 90. If you make a triangle out of it, x is my short side, y is my long side. Natalie's short side is always in a 30, 60, 90. How long? 1/2. Long side?
Square root of 3 over 2.
Square root of 3 over 2. And after a while, this just gets kind of repetitive because you're doing the same thing. So sine is y, cosine is x, and tangent is y over x, but when you divide them, the 2's cancel. Cosecant is going to be 2 root 3 over 3. Secant is going to be 2. And cotangent, you can pretend like there's a 1 there. When you flip it, you get 1 over root 3. And then fix it is root 3 over 3. Now, if you look at the 6 trig functions of 30 and the 6 trig functions of pi over 3, which is 60, all the answers are the same. They just switched places. Sine switched places with cosine. Secant switched places with cosecant. And tangent switched places with cotangent. So those were the way I pronounced them was on purpose. Those are called cofunctions. When you take a function and you put the word co in front of it, it's the cofunction. And that's what switched places, all the cofunctions. Questions on that? All right, let's try 135. This time, just the sine, the cosine, and the tangent. All right, so now we're in a different quadrant. All right. So when you have an angle that's not a quadrantal angle, okay, you've got to figure out the coordinate based on the right triangle. It's either going to be a 45, 45, 90 triangle or a 30, 60, 90. To figure out which one it is, ask yourself if 135 is a multiple of 30 or is it a multiple of 45? Huh? It's a multiple of 45. So if I draw my angles, 135 is exactly, yep.
It's just going to be like, yeah, like that. Never mind.
So where would 135 go? Yep.
It's exactly between 90 and 180.
Yeah, 35 is right here. So here's your triangle. Right. From 90 to 135 is how much? 45. So this part outside right there is 45, which means this part inside has to be a 45. Right? So you went 45 degrees past 90, that's outside, and then you go another 45 to make the quadrant a 90. So that's why it's a 45, 45, 90. How long is each side in the 45, 45, 90? They're both root 2 over 2. Now, when we write the coordinate, what do we have to be careful about? Negatives. Okay. They're both root 2 over 2, but you went left and you went up. So what's going to be my x value for this coordinate? Negative root 2 over 2. And my y value? Root 2 over 2. And now the answers you get when you use other quadrants are pretty much the same answers, except sometimes they're negative. That's all. So this time, one of them's negative and one of them's positive. They're not the same. So if you mix them up, we're going to get sine and off. How about, Joe, what's the sign here?
Square root of 2 over 2.
Yes. Square root of 2 over 2. My cosine? Yep.
Negative square root 2 over 2.
Negative root 2 over 2. And my tangent, I'm dividing the sine by the cosine. So what's my tangent? Chris?
-1.
-1. And if you wanted the cosecant, the secant, and the cotangent, all you would do is take those and do what? Reciprocal. Flip. So there's 135. Let's look at this one. 7 pi over 6. Well, for me, I think better in degrees. Pi over 6 is a basic one. Does anyone remember what pi over 6 is? If you don't, you can always go back to converting it the long way. Multiply by 180, divide by pi. But if you remember this, it'll be a lot faster. It's 30 times 7. So what's 30 times 7? 210. So now we have to decide if it's a 30, 60, 90 or 45, 45, 90. Is that a multiple of 45?
No.
No. Is 210 a multiple of 30?
Yes.
Yeah, it's 30 times 7. We just did that. So 210 degrees. If you try to sketch it accurately, it's a little bit past 180. Down here. Let's make a triangle. Draw your hypotenuse. Draw your other side. And now I can, again, pretty easily tell which side is the long side and which side is the short side. Long side is always, Gabe, what number is the long side? Can you say it one more time? Yeah, there you go. Square root of 3 over 2. And this time we went left. So just make sure it's negative. And the short side, it's also negative. And how long is it? Oh, Ryan?
1/2.
1/2. And then again, because it's down, make sure you put it negative. And now we can go through the sine, the cosine, the tangent. So there's your sine, cosine, and the tangent. Well, let's see what's going to happen. 2's cancel when you divide. The negatives cancel. But we have to fix that. Root 3 over 3. Yep. All right. Any questions on that? All right. So at this point, there's, let's see, 16 different points I could ask you to find coordinates for. You can do the 30, the 45, and the 60 in each quadrant. So there's 3, 6, 9, 12. And then you can do the basic ones, 0, 90, 180, 270. So there's 16 different points, and each point I could ask you for one of 6 trig functions, the sine, the cosine, and so on. So any questions on that? Okay. So if you have to evaluate a trig function that's not a multiple of a 30 or 45, like 17.4 degrees, we can't do that on the unit circle. We can only do ones that are multiples of 30 and 45. And technically, you can also do the 15s. So we don't know the trick to do the 15s yet. We are going to learn it much, I think, in chapter 7. But for now, anything that's not a multiple of 30 or 45, we use the calculator. So I could have had the calculators out for this part, but I think it's basic enough you can watch. Okay, so we're going to find all 6 trig functions of 42 degrees. First thing I have to do is look at my calculator and decide if it's ready for me to plug stuff in. If I plug stuff in now, it's going to come out wrong. Does anybody know why my calculator is not ready to do this problem? Yeah?
Does it say radian up top?
Yeah, it says radians. This problem is in degrees. So the problem's not going to say, make sure you switch your calculator to degrees. You have to know, okay, the argument is in degrees. I'm going to put my calculator in degrees. Now I'm ready. All you have to really do is just sine 42 and hit enter. So 0.6, what did they say? 2 decimals, so 0.67. Cosine of 42, 0.74. And tangent of 42, 0.90. Now, is there a button on the calculator that says CSC, SEC, or COT? Well,
You do second and then the one above it.
all right, so you might think, like when you press second and the one above it, usually when you raise something to a -1 power, that means flip it, usually. With trig, it's a little different. When you see a -1 in that spot, it doesn't mean to flip it. If you see any other number in that spot, it basically is like an exponent. But I know it's kind of weird. That -1 is not an exponent. It's a special symbol, which we'll talk about probably in a couple weeks. So the only way we can find these is to do the same thing we've been doing all along. What did we do with the 3 on the left to get the 3 on the right? Take the reciprocal. 1 divided by 0.67. 1.49. Now, it would be a little more accurate if I typed it in like this. 1 divided by sine 42. In this case, it does come out close, but if you type the original problem in, then you're not using something you rounded. Okay, so now flip the cosine. 1 over the cosine. Okay, 1.35. And lastly, flip the tangent. 1 divided by tangent, 42, 1.11. So it would be nice if you could just press second and use that feature, and that's usually what a lot of people guess. But unfortunately, that's just something totally different. But that's a good guess. Any questions on that? All right. Let's just do the first two, the sine and the cosine. How would you read this problem? Yep.
Sine 10 radians?
Yes, sine of 10 radians. So now, well, I have two options. If I had a calculator that didn't do radians, I could change 10 radians to degrees by hand and then do it that way. Or since my calculator does radians, I'm going to change it and do it that way. So it'll always tell you right at the top what mode you're in. So sine of 10, negative 0.54, and cosine of 10, negative 0.84. And again, to find the cosecant and secant, you would just flip those numbers just like we did in degrees. Any questions on that? Okay. So the last thing, and I'm probably just going to give you the formulas today, and then we'll finish it up. It'll probably take about 10 or so minutes tomorrow. When we look at example 6, just go back to it for a second. The only way we could get the cosecant, the secant, and the cotangent was to flip the reciprocal. So sine and cosecant have a special connection between them. Cosine and secant do, and so do tangent and cotangent. And the special connection, the way you kind of formalize it, is they're called reciprocal identities. It's an identity because it's not like it only works some of the time. If you flip the sign, no matter what you're taking the sign of, you always get the cosecant. Always. Right? That's what an identity means. It's a formula that works all of the time. Right? So here's the three that we've been using. If you flip the sine, you get the cosecant. If you flip the cosine, you get the secant. And if you flip the tangent, you get the cotangent. Now, What if you flipped it again? What if you took the cosecant and flipped it? What do you think that would give you? It would change it back to what you started with. That's flipping it again. So if you flip the cosecant, you get the sine. What if you flip the secant? You would get the cosine. And what if you flip the cotangent? You'd get the tangent. The three on the left are really the main identities. The three on the right are just different versions of the ones on the left. If you're saying that, let's call this Formula 1 and Formula 2. If you're saying Formula 1 and 2 are different, then that's kind of like saying that this is different from that. Distance divided by rate equals time. Distance divided by time equals rate. They're really the same thing. It's just rearranging letters. Really just moving things around. Right? So they're not really different. So the three on the left are the main three reciprocal identities. Any questions on that category? So there's certain basic trig identities. This is one category of them. We're going to learn about 5 or 6 categories. So eventually you're probably going to want to have like a page in your notes where you can fit. You'll probably take like a page to put you can put like boxes and kind of organize them. You probably didn't put this on a page by itself, so at some point you'll want to have a page for just identities. All right, so a couple special properties about sine and cosine, but let me see first. You know what? Before I do those, since you just wrote down these identities, let's group together all the identities so you don't have something else and then identities again. So the reciprocal identities are one group of fundamental identities. The next group is called the tangent and the cotangent. And you've really already been doing that. At least I've been kind of saying it. I don't know if you've heard me kind of slip it in a couple times. When I said y divided by x is the tangent, sometimes I said it as sine over cosine. Like I said, I just pretend putting an imaginary line and dividing the sine by the cosine. That's because I was trying to get you to think about it like this. Sine divided by cosine is the tangent. So like if you had a calculator and the tangent button wasn't working, so let's say you couldn't do the tangent of 20. You could do the sine of 20 and divide by the cosine of 20. Sine divided by cosine is tangent. And if you flip it, instead of sine over cosine, flip it, well, you get cotangent. Because if you flip it, it's the reciprocal. Now, the last group of identities, we're not going to do anything with them today or tomorrow. They're not going to be on the test. It's just they're the last basic ones. I'm just trying to get you to put them all in one spot. And they're called Pythagorean identities. And the Pythagorean identities are sine squared plus cosine squared equals 1. One plus tangent squared equals secant squared. And 1 plus cotangent squared equals cosecant squared. Seems kind of weird and you're not really sure why they're true or what's going on there, but those are called the Pythagorean identities. Again, you don't have to worry about those for the test. Okay, so just now if I say flip back to your notes where you have your fundamental identities, you're going to have them all in the same spot. And there's even, like I said, there's more, but those are all the fundamental ones we're doing for now. Any questions on those? Alright, so I'm not going to do that. There's not really much left. I'm going to save those 3 for tomorrow. And the last thing I'm going to mention is what I was going to mention at first. And there's just a couple special properties about sine and cosine. Sine and cosine, we're going to graph them next week. And when you look at them, they look very similar. Sine and cosine, the graphs are almost the same. Here's what sine looks like. And I'll do cosine in red. They both have kind of a wave pattern to them. When you graph any other trig function, tangent, the secant, the cosecant, or the cotangent, they don't look like waves at all. Sine and cosine are the only two that do. And what I'm trying to show you is if you look at the red and the blue waves, how high does it look like they both go?
1.
1. How low? -1. They're always between 1 and -1 on the range. Okay? And actually, technically, you can make that a bracket because it does hit 1 and -1. So that should be a bracket. And the domain, well, they just go left and right forever. If you zoom out, you're just going to see more waves. Right? So they go on forever, left and right. And the last property is a property you've been using, like if I asked you to do something like this. That's too big, right? It's too big to think about in our head. So what would you subtract from 540 to make it smaller? 360. 540 minus 360, it's actually the same as 180. Well, that property has a name, and it's called the periodic property for sine and cosine. If you want to know the sign of something, that's exactly the same as finding the sign of that something plus or minus any amount of 2 pi. Or if you're doing it in degrees, you could replace 2 pi with 360. You could add 360 times 1. You could add 360 times 2. You could add 360 times 3. And if you're like, well, what about subtracting? Well, just pretend like n is -1. 360 times -1 would subtract 360. 360 times -2 would subtract 360 twice. Right? So this is just saying you can add or subtract 360, or 2 pi, if you're doing it in radians, as many times as you want. And it's just an equivalent way of figuring out the same thing. And that's called the periodic property of sine and cosine. Okay, so tomorrow we'll look at a couple examples with trig identities. So don't worry about those for tonight. So we'll look at those couple. So the homework is page 335, the 1, 5, and 8, and the stuff that I gave you yesterday. And don't worry about the simplified. Let's see. All right, so 13 to 17, that should be fine. You do need a calculator for a lot of it. Like this is just like find the sine of 12, find the cosine of 17. You just have to type them in. And 6. Don't worry about number 50. Okay, so there are no identities in the homework. This is all unit circle stuff. So we'll look at that tomorrow. It'll probably take us about 10 or 15 minutes to finish up, and then we'll review for the test.